To get an airplane to fly, you need wings and air. To drive a car, you need wheels and a road. But now, to get a human into space, we need to build a gigantic metal tube filled almost entirely with rocket fuel, set it on fire, and blast off at 28,000 kilometers per hour. If you go just a little too slow, Earth's gravity is going to drag you right back down to burn up in the atmosphere. And if you go off course by a fraction of a degree, well, you're going to miss your target entirely. You can see why rocket science has a reputation for being the hardest discipline on Earth. But when you strip away the high-level math, it comes down to 5 massive engineering problems. And today, we're going to be breaking down to see how rockets actually work. Well, let's start off with the single biggest headache in aerospace engineering: the weight of fuel. In a normal car, you fill up the gas tank to carry the weight of the car, the engine, and the passengers. But in a rocket, the fuel itself makes up almost all of the weight. Think about it this way. To lift a heavy rocket off the pad, you need a ton of fuel. But that fuel adds massive weight to the rocket. So to lift that extra weight, you need even more fuel. And to lift that fuel, you need even more. You can see that this is a brutal cycle. Because of this, roughly 90 to 95% of a rocket's total weight is liquid propellant. The actual spacecraft, satellite, and astronaut sitting at the very top, what engineers call the payload, makes up less than 5% of the entire vehicle. So, how do you get enough power out of all of that fuel to push up a gigantic metal tank into the space? It comes down to the Newton's famous third law. If you blast hot gas out of the bottom as fast as humanly possible, the rocket shoots upward in the opposite direction. But getting gas to move fast enough, it's tricky. To do it, engineers use an engine nozzle shaped like an hourglass. The top is the combustion chamber, where the rocket fuel and oxygen mix together and ignite, creating extreme heat and massive pressure. In the middle is the pitch or throat. As the expanding hot gas gets squeezed to the narrow neck, it speeds up until it hits Mach 1, which is, as we all know, the speed of sound. The bottom is the expanding bell. Once it squeezes past the bottleneck, the nozzle widens back out. And counterintuitively, expanding the space does not slow the gas down. It accelerates it into supersonic speeds. The faster the gas blasts out at the bottom bell, the more efficient and upward thrust the rocket gets. Even with super fast engines, a single rocket cannot make it all the way to space, carrying all of the heavy metal tanks. So engineers use a trick called staging. Once the bottom half runs out of fuel, those massive engines, heavy pumps, and empty metal tanks become useless dead weight. Instead of dragging all of that metal to space, the rocket detaches its entire bottom section and lets it fall into the ocean. Now, a second, much smaller engine lights up. Because of this, no longer has to drag that entire lower structure along. It easily accelerates the payload the rest of the way to orbital speed. And how do rockets steer in the vacuum of space? They use something called gimbaling, where the hydraulic pistons physically tilt the engine nozzle left or right, directing the superfast exhaust to steer the rocket. Here's a common myth. People think rockets fly straight up into space to escape Earth's gravity. But if they did that, the moment the engines turned off, gravity would drag it back down. To stay in space without falling down, you don't just go high. You have to go fast, sideways. When the rocket launches, it climbs to a minute or two to clear the thickest part of the atmosphere. Then, it tilts to its side in a maneuver called gravity turn. By flying horizontally around the Earth at 17,500 miles per hour, the rocket is essentially falling towards Earth, but moving so fast, sideways, that the ground curves away beneath it, at the exact same rate. That continuous state of free fall is what we call orbit. For over 6 decades, every rocket launch meant throwing away millions of dollars worth of engines and hardware after a single flight. Today, engineers are flipping that script. By combining supersonic grid fins, thrusters, and real-time computer math, we can now land a 15-story rocket booster vertically back on Earth to refuel and launch them again and again and again. So, thanks for watching, and if you enjoyed the video, leave a like and consider subscribing, and see you in the next breakdown.